Number 13 is I can apply the exponent laws to powers with both integral and variable bases. So here I have drawn out all 5 laws: the quotient law, the product law, the power law, the zero exponent law, and the negative exponent law. So, starting with the quotient law. Here we have the question of 3 to the power of 8 divided by 3 to the power of 6. So what we do first, according to our quotient law, is we keep the base. So here the base is 3. We subtract the exponents, so 8 and 6, 8 minus 6, and we divide the coefficients. But in this question, there are no coefficients, so that is irrelevant. So 3 to the power of 8 minus 6 is equal to 3 to the power of 2. So 8 minus 6 is 2. Then 3 to the power of 2 is 3 times 3, which is 9. Now, as a variable base, we have x to the power of y divided by x to the power of z, which is equal to x to the power of y minus z. We also have x to the power of 20 divided by x to the power of 16, which is equal to x to the power of 20 minus 16, which is x to the power of 4. Now onto our product law. First thing we do is, so in this question, of 3 times 2 to the power of 4 times 7 times 2 to the power of 4, first thing we do is we keep the base. So the base for these exponents are 2. So we keep the base of 2 and write it down here. Next, we add the exponents. The exponents are 4 and 2. So 4 plus 2 is equal to 6. Then we multiply the coefficients. So here we have coefficients 3 and 7, and 3 times 7 is 21. Now we have this, and we do 2 to the power of 6 is 64, and 64 times 21 is equal to 1,344. Now as a variable base, it can be x to the power of y times x to the power of z is equal to x to the power of y plus z. Or you can do x to the power of 12 times x to the power of 3 is x to the power of 12 plus 3, which 12 plus 3 is 15, so it's x to the power of 15. Now we have our power law. Our power law says we keep the base and multiply the exponents. So here our base is 3, so we keep that, we write 3 down, and then we multiply the 2 exponents, so 2 and 4. 2 times 4 is 8, so we have 3 to the power of 8, which is equal to 6,561. As a variable base, that can be x to the power of y to the power of z. This is equal to x to the power of y times z. We can't go any further than this because we don't know the value of these variables. Now we have this, x to the power of 5 to the power of 7. So we keep the base of x and we multiply the 2 exponents, so 5 times 7, which is equal to x to the power of 35. Next we have our zero exponent law. So remember, in our zero exponent law, any number to the power of 0 is always equal to 1. So here we have 120,370 to the power of 0, which is still going to be equal to 1. That means that even if we have x to the power of 0, even though we don't know what x is, we still know that no matter what it is, the answer is going to be 1. Now we have our negative exponent law. So if we have a question like negative 5 to the power of negative 2, our negative exponent law says we find the reciprocal. So negative 5 is the same thing as negative 5 over 1. So to find the reciprocal, we have to flip the 2. So when you flip it, it equals negative 5 over 1. So I'm just going to erase this here. And once we have the reciprocal of this, we can turn the exponents into a positive exponent. So negative 5 to the power of negative 2 is equal to 1 over negative 5 to the power of positive 2, which you keep the 1 there, and negative 5 times negative 5, because negative 5 to the power of 2, is equal to 25. So the answer is 1 over 25. Now, we have it in variables. X to the power of negative y, x to the power of negative y, and that would equal, because x is the same thing as x over 1, but that again is irrelevant because that is, we all know that. So the reciprocal is 1 over x, and then the y changes to a positive y. So the answer to this would be 1 over x to the power of positive y. Now here, we would have x to the power of negative 6, which the reciprocal of x is 1 over x to the power of positive 6. So this x to the power of negative 6 is equal to 1 over x to the power of positive 6. And this is how I can apply exponent laws to powers with both integral and variable bases.